Good morning, everyone. This is Shauna, and I'm here today to record a shorter video on section 6.3, which is dealing with the central limit theorem for sample means. Okay. So let me get into this a little bit by way of the slides. So what happens is that in the sections before this, we were talking about samples that come from populations. Remember that a sample is representative of a population. And with a normal and a binomial distribution, we were talking about individual data, okay? One person's IQ, one CEO's age, one child's weight. Now what we're doing is we're taking that same concept and we're asking about the probability that a sample of 30 children has a mean weight of something, or a sample of 50 CEOs has a mean average of something else, a mean age of something else. That's what we're doing here. And so our formula changes slightly, but the process is very similar. Before we get to that, though, we have a terminology for this. It's the sampling distribution of sample means. So we still have a normal distribution, okay? Let's assume, for the sake of example, we're going to be focused on this normal distribution. We're going to come back to this assumption in a minute. But instead of having a number here or a zero here, we're going to have, instead of having a population mean here like we're used to, we're going to have a sample mean. And what that tells us is that we've taken all the samples of whatever size, 5, 10, 27, 85, whatever it is. We're going to have a sample mean in the middle here, okay? And so the formula, the z-score formula that you're going to see in a couple of slides, instead of being keyed to the individual numbers, when it looks like this should look very familiar to you, x minus mu over sigma. Instead of looking like this for an individual, we're going to generalize it to a sample. And so what we're going to do is we're going to write our sample notation. So we're going to have x bar there. And we're going to divide this sigma by the square root of our sample size. And that's going to be our new z formula. Okay. Everything else is going to stay the same in terms of shading areas and doing all of that. But that's where this is going. So let me, at this time, go to the homework. Now, if samples of a specific size are selected from a population and the means are computed, what is this distribution of means called? I just told you, it's called the sampling distribution of sample mean. So you're going to write for this first question, you're going to say that this is the sampling distribution of sample means. That's what this is called, okay? Now, it has some properties, okay? It has some properties, and I'll show you those on the slide. But the mean of the sampling distribution of sample means equals the population mean. Now, this could be counterintuitive for you. You're like, well, how can it be the population mean if we're not testing everything in it? But this essentially what it is we are, because we're taking all samples of that size. So we're actually taking every value in theory. And so the mean is equal to the population mean. And then what does the central limit theorem say about the distribution of sample means? Let me show you that. I'm gonna stop sharing this screen right now so you can see the writing disappear. And you're gonna see me switch gears back to the slides. Now, the distribution of sample means will be approximately normal. Remember, normal refers to the shape of the distribution, it's spelled shape, for larger sample sizes. The mean of the sample of the distribution of sample means approaches the population mean. That is, mu of x bar, this is the mean of all the sample means, is equal to mu sub x that I got from the x variable. And the standard deviation is sigma over the square root of n, and so forth. So that's kind of what I was showing you here. Okay, now the next thing it says is, what does it say about the size of the sample itself? Here's my formula, which you've already seen. Here's what it says, okay? For practical purposes, the distribution of sample means will be nearly normal if the sample size is greater than or equal to 30. If n is less than 30, then the individual original variable should be normally distributed. Now, the original variable, and by that she means the population from which it came. The essence of the point here is that if your sample size is bigger than 30, then you're going to get a normal distribution of sample means, unless your parent distribution was extremely skewed. It would have to be extremely skewed for you to need more than 30 samples. If you have a parent distribution, like the population was normal, if that's given to you, then the sampling distributions that derive from that will of necessity be normal. So if you start with something that's normal and you extract samples out and you create another distribution, that has to be normal. If you start with something, let's say, right skewed, and you don't take enough samples out of it, maybe you only take 10 or 12, then chances are that's not going to be normal and this technique is not going to work. But if you start with something normal, the distribution of sample means from that will always be normal and will always be bell curve. Okay. So that brings us now to the example from the homework that I wanted to do for us here. Okay. I'm going to do this example for us. I'm going to share the screen. And we're going to do number 4. We've talked about the first 3. I'm going to talk about number 4 here. The average weekly unemployment benefit in Montana is $272. Now, whenever you read a problem in statistics, especially from here on out, I want you to go on the saying that everything means something. Every shred of something means something. So here, the average weekly unemployment benefit in Montana is 272. Suppose that the benefits are normally distributed with a standard deviation of $43. A random sample of 15 households. Okay, now, what is the probability that, so here's my question, what is the probability that, there's my question, right? That the mean for this sample is greater than the US average, which is 299. So that's a lot of information to take in. Let's break it down. Average, this word, when you see it, signifies the mean, okay? So we have this. We know that mu so here we have mu is equal to 299. $299. We know that X bar is 272. So we're going to take this and put it in there. We're going to have equals 272. We also know that we're going to have sigma is equal to 8. And then your sigma here is 43. Now, what we're going to do is we're going to calculate our z. So I'm going to go to my calculator here. Go to my calculator screen, clear my formats, and I'm going to say, I usually like to start with parentheses. So we have 299 minus 272. So we have 299 divided by 2, subtracted from 272, and we're dividing that by This is going to be 43 divided by the square root of 15. So there's my calculation. And there it is. There's my 3. So now, how does this look? Now we're going to find the probability. But let me do something here. I'm going to stop sharing the screen. And I'm going to share a whiteboard. So how would I do this? The first thing I would do is I would go ahead and write out your given information. So the first step, we're going to write, you're going to write the givens, right? Given information, okay? Now, what did they give us? Well, they gave us mu, which is 299. They gave us X bar, which is 272. This is equals 272. They gave us sigma, which is 43, and they gave us n, which is 15. Then I'm going to put it in my formula, okay? So the next step is I'm going to you can draw a picture at this point, or you can put it in the formula first. Some people prefer to put it in the formula first so that they can figure out where the z-score is. So we're gonna have, I'm gonna draw my picture after I put it in my formula. Z is equal to X bar minus mu over sigma divided by the square root of n. So we get now we're gonna have 299 minus 272 over, we're gonna say over 43. This is gonna be 43 here. 43 divided by the square root of 15. So this is going to be This is going to be 15 here. So I've got this situation going on. Okay. Now, if you put this in the calculator, as I have already done for you, this comes out to 2.43 if I give you two decimal places. This is my Z. Now, the reason that I suggest that you do that is so that when you plot your curve, which remember she has to see your curve, this is going to be your X bar, which is 272. And you're looking at, this is going to be 272 here. $272. Then this would be my X, but this would also correspond to my Z of 0. So what I'm going to do here is I'm going to show two separate lines on here. Let me actually do something. I'm going to go and erase my, I'm going to show you something here. I'm going to erase this. Maybe I'm not. Maybe I'm gonna. Okay. Let me see if I can. This, I'm gonna write this as, this is gonna be my, this is gonna be a situation where I just wanna write this out differently for you. So here's my, this is my pen here. And I'm gonna say that this is, now what some people, I have no idea what's going on with this, so I'm gonna close this and do it here. I'm gonna do it on here. I realize you're not gonna have as much space, but having issues with the Zoom whiteboard. So what I typically do is I typically have a Z and an X. So this is gonna be my X here. And underneath it, I'm gonna have a Z line. And that's just easier for me when I'm doing it. And I'll show you why in a minute. This X is going to be 272, as I've told you. This is 272 here. This Z is going to correspond to a Z of 0. V equals 0. That's my X is 272. My Z is 0. So when I set this up, see if I could show it better over here. Maybe this will show up better. This is going to be, there's my X line. There's my Z line here. Now, we know this is 272 right here. We know this is 299 over here somewhere. So this line is here, okay? And we're going this way, dating to the right of it, right? This Z corresponds to a Z of the Z that we got in the calculator, which was 2.43, okay? So this Z is 2.43. Now, this Z, that's 272, that corresponds to a Z of 0. This is why we had our Z-score. So now we converted that. This is my Z line. So we have my diagram, right? And now we're going to go ahead and plug it in. So the next step is to show your calculator. So I'm going to go ahead, and my last step is going to be to share the screen, share the calculator here. And I'm going to go to second distribution, just like in 6.1, normal CDF number 2. This is positive 2.43. I'm going to delete that. 2.43 E99. Paste it. And there's my answer, 0.0075. So my answer for this question, what is the probability that the mean of this sample is greater, is going to be, let me put it on the screen, okay? So I have probability of there it is. Draw. So I have probability of X bar greater than 299 is equal to the probability 99 is equal to the probability of Z. This is the probability of Z greater than 2.43, 2.43, which is equal to, here we go, normal CDF from 2.43. Remember, this is a Z now, so we have 0 and 1 as my mean and my standard deviation. And when I do that, this answer is going to be equal to this answer is going to be equal to 0.0075, which is 0.75%. Okay. Most of the rest of these problems are very similar. There are 8 of them left on here. So that should get you started with knowing, but the only difference really is figuring out which mean is which and figuring out your normal CDF with your sigma divided by the square root of n. Now, there is one other aspect to this problem. Is the normal distribution appropriate here since the sample size is only 15? Yes, it is, and here's the reason why. It says, suppose that the benefits are normally distributed. They came from a normally distributed population, so therefore any sample that comes from that will also have to be normally distributed. If it were not true, then you could not assume that. If you look, for example, at number 5, the mean undergraduate costs of tuition, fees, room and board for 4-year institutions was this number for a recent academic year. Suppose that sigma is 3,204 and that for 36 4-year institutions randomly selected. Now, nowhere in there did it say that that group was normally distributed, right? So because it didn't say that, the sample size has to be larger than 30, and it is. So you can use the sampling distribution here. Be very careful with those assumptions. Everything means something. That's all I have for now, guys. I'll see you in my next video. Thank you for watching. Bye for now.